Hello everyone, my name is Adnan Munawar and I am a postdoc fellow at the Lab for Computational Sensing and Robotics at the Johns Hopkins University. I am excited to present our work titled A Framework for Customizable Multi-User Teleoperated Control. Teleoperated control or teleoperation comprises of the control of a robot or a machine at a distance. This type of control is advantageous for high-risk applications. A practical example is that of the Da Vinci surgical system, which allows a surgeon to teleoperate robot manipulators for performing surgical procedures. This setup complements the skills and the intelligence of the surgeon with the precision and safety provided by the robot. Shown in the image is a research version of the Da Vinci surgical robot, aptly called the Da Vinci Research Kit. The surgeon interacts with physical input devices and a stereoscopic heads-up display to control remote manipulators. Just like the remote manipulators serve as physical proxies for the surgeon's hand motions, a remote camera serves as the proxy for the surgeon's visual perception. The goal of the teleoperation system is to allow hand motions that appear correct or calibrated with respect to the surgeon's or the operator's view. What this means is that both the linear and angular motions should appear correct regardless of the change in the pose of the remote camera. This is also referred to as the hand-eye coordination. It is also desirable for certain applications to have force feedback on the input devices that results from the remote robot interacting with the environment. Since several intermediate components are involved in the teleoperation scheme, achieving hand-eye calibrated motion requires the knowledge of the hierarchy of individual components and the proper coordinate frame assignment to each component. As shown in the image, coordinate frames are assigned to the input device's base and tip, the heads-up display, the remote camera, and the remote robot's base and its end effector. With this arrangement, one would require two additional transformation matrices to align the linear and angular mapping of the input device with the remote end effector. These two matrices are convoluted as they are affected by all the higher-up components in the hierarchy. The remote side camera and robot manipulators are usually mounted on a cart, such as the one shown in the figure. Thus, all the intermediate transforms are resolved using the frames assigned to the links of the cart and solving for the kinematic chain. Even with the common frame at the remote site, multiple different configurations must be accounted for to achieve a hand-eye calibrated motion. As shown in the image, different remote cameras can be used for different tasks, thus requiring different mapping transforms. Likewise, the tools that are the end effectors can have different angular offsets with respect to the input devices. For example, the cautery spatula with its tip frame as shown in the image has a different mapping transform compared to the large needle driver. Controlling a simulated robot using a physical input device is in many ways similar to the teleoperation of a remote system. In this regard, simulators offer a low-cost solution to carrying out user training and prototyping a teleoperation system. There are several popular community simulators such as Gazebo, VREP, and Mojoko that support the robust simulation of robots, mechanisms, and bodies. Unlike commercial platforms, different input devices can be used to teleoperate different simulated robots for different tasks. This choice results in the description of new mapping transforms for each combination of an input device, simulated robot, and camera pose. An example of requiring different mappings is shown on this slide. The two robots on the left have a similar configuration but different base and tip frames, thus would require different mapping matrices. On the right, a single end effector is shown which, depending upon the application, could be mapped to the input device in three different ways, thus also requiring three different mapping matrices. What if we were to pair multiple input devices to a single robot such that each input device can teleoperate some or all the Cartesian degrees of freedom of the robot end effector? We call this as multi-user or shared teleoperation control. Shared teleoperation control opens up interesting possibilities of remote manipulation, user training, and safety. The shared teleoperation control problem does not limit operators to perform in different view frames. As shown here, user A has a natural hand-eye alignment with the robot and user B does not. However, User B may be able to perceive obstacles that user A cannot. Both the users should be able to teleoperate the robot and feel the force feedback in their view frames. Furthermore, the force feedback should be disconnected between the two input devices. To justify this, imagine an example where the robot is in contact with an obstacle. The user trying to drive the robot further inwards should be the only one receiving an opposite force. For the remainder of the slides, we are going to be using the following terms. An input device will be referred to as an IID, and the end effector shall be referred to as an SDE. A triplet of an IID, SDE, and the view frame is called a telerobotic unit. We also borrow the concept of clutching from the Da Vinci surgical robot. Clutching is used to engage and disengage the motions of the SDE upon the trigger of a certain event. A clutching scheme also exists for the camera control via IID. Summarizing the problems discussed in the previous slides, we arrive at the formal problem statement. Our goals are as follows. Number 1. Pair different input devices to different end effectors in customizable camera frames. 2. Pair multiple input devices to a common end effector in shared or independent view frames. And 3. Allow continuous motion engage and disengage of end effectors and cameras. Several challenges need to be addressed for a simulation framework that allows multi-user teleoperated control. The first challenge is the architecture of the simulator itself. The simulator must be capable of incorporating multiple input devices with different update rates, with high-speed communication requirements, and be able to generate force feedback. Next, the simulator should provide an API that allows for defining the mapping transforms for different telerobotic units without the need to write and compile code. Last but not the least, the simulator must provide the means to pair multiple IIDs to SDEs. As discussed in the problem statement, a robust simulator is required to interface multiple IIDs with high-speed communication requirements with a real-time dynamic simulation. Since many community simulators are not designed with haptic interaction in mind, one has to utilize their plugin-based API to interface IIDs. The sequential nature of this API causes circular deterioration of the haptic and dynamic updates. Shown in the slide is an example of such a sequential pipeline where 5 input devices with a required update rate of 1 kHz are run with a dynamic simulation also required to run at 1 kHz. Based on the computational complexity, we can see that it is infeasible to maintain the desired update frequency. We designed the asynchronous multi-body framework with this limitation in mind. AMBF allows the pairing of multiple input devices with different update rates with a real-time dynamic simulation. In addition to this, AMBF is a robust simulator that allows the simulation of robots and mechanisms which are defined using the AMBF description format. Shown in this slide is an example of 5 input devices interacting with the real-time dynamic simulation. Due to the asynchronous design of AMBF, the haptic devices can update at the desired frequency and thereby taking the load off of the generally expensive simulation loop. In AMBF, the pairing of IIDs to SDEs is modularized. Instead of defining mapping transforms between the two, we map the IID to the simulation world. This is done by introducing 2 coordinate frames called IBO and ITO. At the remote side, 2 more frames are used for the SDE, which are called SO and STO. In total, these are 2 more transforms compared to the earlier example of DVRK. However, these transforms modularize the specification process and are easier to comprehend. While only 4 mapping transforms are user specifiable, there are a total of 8 coordinate frames and 8 transforms associated with each telerobotic unit. The frames and transforms are divided into 3 categories and are color-coded on the slide. The 3 categories of frames and transforms include implicitly specified or beyond user control, explicitly specified by the user, and proxy or caching transforms that modulate the control laws affecting teleoperation and force feedback. We show example of defining the explicit frames in this slide. The orientation of the simulation world frame is fixed with respect to the user. With the user holding the IID at the desired home position, place two frames oriented similar to the W frame at the IID's tip location. One is defined with respect to IB and the other with respect to IT. For the SDE, place and align the mesh as is desired using the frame SO. Then place a frame oriented similar to W frame at its mesh location. This is the frame STO. Now simply compute transformation between these three frames and their respective parents. The frame STO is responsible for defining the orientation or angular mapping between the IID and the SDE. The video shows example of changing this frame. The coordinate frames and transforms are complemented with the control algorithm discussed here. This algorithm is executed asynchronously for each telerobotic unit. If we consider the teleoperation scheme as a system, the inputs are the post changes of the IID, and the output is the force feedback emanating from the interaction of the SDEs with the environment. Looking at the control laws from the last slide, we use a 3D vector for stiffness and damping gains for the linear and angular inputs and outputs. By calling the gain vector disabled if it is a zero vector and calling it enabled otherwise, toggling these gain vectors, we can achieve various modes of shared control as shown on the table on the right. The gain vectors and the pairing relationship between the IID and SDEs are defined using the YAML-based ADF files, which skips source code modification and recompilation. The field called simulated multibody is a file path of an ADF file that describes a robot mechanism or a single body. The field called root link refers to the name of a body that serves as the base of the SDE that is paired to the IID. If simulated multibody field is defined, the root link is searched locally in that file path, and if not defined, it is searched globally in the simulation. Thus, by using the combination of simulated multibody and root link, single or shared teleoperation control can be set up. We validated the framework by conducting a user study. 5 human subjects were enrolled for participating in a shared teleoperation experiment. The study participants were tasked with controlling the DBRK MTMs to perform 2 different manipulation tasks. The first manipulation task involved picking a peg with one SDE, hand over in between, and placement on the opposite end. The second manipulation task involved bimanual manipulation of the multibody and its insertion on a matching extruded base. Each manipulation task was first performed independently by the participant and then with shared teleoperation guided by a master operator with and without force feedback. The master operator interacted using an Owen Falcon IID with only the position control of the SDEs. The participants were allowed to train on each task before the study. 3 of the 5 study participants had less than 2 hours of prior experience with the DBRK. The task performances were evaluated based on the NASA TLX metrics. The results indicated the preference of the users for shared teleoperated control as compared to independent control with a higher preference for shared assistance without force feedback. Other metrics collected for the study included the path traversal length of the participating IIDs, the task completion times, and the clutching frequency. Shared teleoperation with no force feedback resulted in lower task completion times, clutching frequency, and IID path traversal length, while shared teleoperation with force feedback fared better than independent control in general. We conclude as follows. We have presented an open source framework that interfaces various input devices with a real-time dynamic simulation. The framework simplifies the pairing of input devices to simulated end effectors by reducing the basis and number of required transformation matrices. It also allows the customizable pairing of multiple input devices to simulated end effectors in shared or independent view frames. In terms of future work, we plan to replace the PD control laws with model-based control law for the SDE control and haptic interaction. We also plan on conducting user studies with different tasks and a higher number of study participants. Finally, we would like to thank the following entities for supporting this work.